Well, it's already 11 and I think we can get started. I think more people are joining on their way, okay? So from this class, we're going to learn a new topic, and that's about the water quality, right? So as you know, for this class, I would say that we will spend maybe more than half of the time talking about water treatment and wastewater treatment. Basically, if you recall what we have gone through, so we talk about the fundamental chemical theories. That is also the major contents for our first exam, right? And then starting from this class, we're going to talk about water systems and also introduce the water treatment, basically the drinking water treatment and wastewater treatment. Okay, so that's going to take maybe half of the semester's time on these contents. This class, basically, we're going to finish on the hydrology and then start a little bit about the water quality in rivers. So this is the reading assignment. That's the chapter 9-3, right? So you can use your time off the class to read them. So just a quick recap of our last class. I did receive a few emails about how am I going to grade the exam. So whether I will provide the partial credits. So I think for the single choice questions, it's quite unlikely that I can give you partial credits, right? So it's just one answer there. But for the calculation problems in part 2, I will give you partial credits. For example, the first problem on the alkalinity calculation, if you just show the equation, right? The alkalinity equals to the concentration of bicarbonate ions plus twice of the carbonate ions plus OH minus hydrogen ions, right? So if you just show this equation, you'll get half of the scores. Okay, so that's 3 points. Basically, this is the way I grade the homework and also the exams, right? So I think for the first problem, the rest of it is try to convert all of the mass into the molarity, right? So those are extra calculations. So some of you also asked me whether we could change the percentage or have a makeup exam. So basically the way I did this, I also did this last year, is that if you see the syllabus, so each of the exam takes 15% towards your final score, right? So if you didn't do well for one of the exam, what we can do is we can lower that percentage to 10% and then increase the percentage of your best exam to 20%. Okay, so in this way, you can change the percentage in there. So I will make the final adjustments after we finish all the exams. Okay, so then I basically want to get some thoughts on the first exam. So I'm just launching a pool. All right, so this is not about the participation, but just to get your feedback on the first exam. So yeah, let me just try to get your response here. So what do you think of the first exam? Okay, so we just share the results. Yeah, so you can see the responses over the difficult region there. So I think, again, it's probably mainly because the first part is about chemistry. And I know that many of you are civil engineering students and you haven't dealt with these chemical definitions for a long time. So later on, as we go to the detailed designs of water treatment and wastewater treatment systems, so the understanding, well, the engineering backgrounds will start to play a role in there. So maybe at that time, the exam will look better. Okay, so it's going to be, I feel that the problems are going to be easier in those areas, because then those are mainly about the designs or let's say the flow rate calculation and things like that. Okay, that's the information about the exam. Oh, so I received a message from Mar. So For the written homework, you can drop it off at the door of 207. So that is 2 doors on the right of our classroom. Okay, so the TA has already left a folder there, so you can drop off your homework there anytime during the day. That will work. All right. Any other questions? Okay, so coming back to the recap. So last class, we mainly talked about the risk assessment, right? So we did some simple calculation about the risks associated with, let's say, cancer or COVID-19, right? And those are about the death, right? So there are also risks associated with chemicals, right? So that's why we give the definition of LD 50. That is a lethal dose 50, right? So that's the dose that's corresponding to 50% of the death to, let's say, to a test animal or some bacteria in there. So also know that the lower the LD 50, the more toxic, right? The more lethal the chemical is. So we also cover the hydrology, mainly on the definition part, right? For example, the watershed or the basin. So basically, these are just water systems that can be treated as isolated from the entire environment, right? And then there's also hydraulic gradient. So basically, this is for the groundwater, where let's say if this is the ground, and then for the groundwater, there is a difference in the height, right? We know that this is basically the saturated soil. So if there's a height in the, if there's a difference in the height, right, delta H, right, you can calculate the gradient by just using delta H divided by L, right? That's the gradient. And then with this gradient, we can also calculate how fast the water is going to flow in the saturated soil. It's going to flow from the higher location to the lower location, right? So basically, you will need to know what is hydraulic conductivity. So how fast this medium is to allow the water to flow through the medium, right? So we can calculate an average velocity. So that is called the Darcy velocity by using this Darcy's law. So that is done by using basically the velocity is equal to the hydraulic conductivity, the K, multiplied by the hydraulic gradient. Okay, so a simple multiplication there. So I think in the exam, you also had the question on that, right? So you have the conductivity, you multiply that by the gradient, and the gradient is calculated by dividing the difference in the height by the L, right, the distance. So then after we know the average velocity, then people also will care about what is the actual velocity of water in there, right? So if you have a medium that's, let's say, so the water is flowing this way, if it's a tube, right, then the average velocity is just going to be the actual velocity. But if you have soil that's packed with the sand particles, then we know that the water is not going to flow anywhere, right? It's only able to flow through the porous part, right? For example, if you look from this angle here, right? Like, let's say the cross section of this soil here, then we know that in this soil, there's going to be all types of sands, some larger ones, some smaller ones, right? So water is only able to flow through this open area. And because of that, the actual velocity of water is going to be higher than the Darcy velocity, okay? So that is calculated by just using, let's say, the actual velocity is just the average velocity or the Darcy velocity divided by the porosity. Okay, so let's take a quick calculation on this this problem here. So you don't have to pull out your calculator. So this is just trying to look at the problem again. I think we covered this problem in our last class too. So this is saying that you have a confined aquifer, right? And then it has 2 monitoring wells. So basically it's showing that the distance between these 2 wells are 500 meters. And then the difference in the water level is 2 meters, right? So you know the delta H, right? You know the distance, that is the L, right? And then it's giving you the hydraulic conductivity, that's 50 meters per day. it wants you to estimate what's the Darcy velocity. So basically here it's not about the porosity yet, right? So the Darcy velocity, as we showed earlier, is just delta H divided by L. This is the hydraulic gradient. And then you multiply that by the hydraulic conductivity, right? So you can see the solution here. That is basically 2 meter divided by 500 meter, you get 0.004. And then you multiply this gradient by the conductivity, where you can get the Darcy velocity, that is 0.2 meter per day. Okay, so this is Darcy's velocity. And then, as we said, so for the actual sand or actual soil, you have a lot of sand in here, right? So the water can only flow through these open area. And because of that, the actual velocity of water, it has to be dependent on the porosity of the soil, right? So for example, let's say if the water has the same Darcy's velocity over these two medium, right? Let's say medium 1 and medium 2. So medium 2 has a larger porosity, right? If it has a larger porosity, then the actual velocity of the water is going to be lower. And for medium 1, this one has a lower porosity. Let's assume that this is, let's say 1%, and this is 10% in terms of porosity. Then the actual water velocity is going to be the Darcy velocity divided by 0.01. That is 100 times of the Darcy's velocity. While for this type of soil, it's just 10 times of the Darcy's velocity, right? So the actual water velocity is going to be higher for more densely packed soil. But of course, we know that in terms of actual soil, they're going to have this type of geometry, right? So you're going to have a few larger grains, right? And then the pores are going to get filled by these finer sand particles, so that the actual velocity is actually even lower compared to the ideal situation. So then you may wonder, why do we need to know this linear velocity, right? Isn't the Darcy velocity good enough? So people typically use this linear velocity to estimate how fast a pollutant can travel within the groundwater. So if you recall in our introduction class, right, so we said that in California, people put in the chemical called the MTBE, right, into the gasoline, right? So the gasoline mainly try to deal with the air pollution problem, but later people realized that this is toxic, right? But at that time, people already found that the MTBE can get into the groundwater. It's very difficult to remove them, right? And then we'll wonder, well, if I just leave 100 meters from a gas station, will my drinking water get impacted, especially if I dig a well into the ground, right? So will the pollutant be fast enough that it can travel to my well so that it affects my drinking water, right? So people need to know the actual velocity of these of the water and the pollutants to make estimations on how fast these pollutants can travel. Okay, so let's get back to this example here. So this is still about these two wells, right? They're separated by the 2 meter, and in terms of height, and in terms of distance, that's 500 meter. So now let's assume that this aquifer becomes contaminated in the upper well. So basically, there are some chemicals dumped into this first well here. So then, as we know, the groundwater is going to flow from the higher location to a lower location, right? And then if we know the porosity, so how do we estimate, let's say, how long after the contamination would you expect the drinking water to be contaminated in the second well? Okay, so how long will it take for these contaminants to flow for this 500 meter here? So then this is related to the actual velocity, right? So as we already calculated earlier, right, the Darcy velocity is 0.2 meter per day, right? And then regarding the movement of the water, we must use the actual velocity or the linear velocity. So that is calculated by the Darcy's velocity divided by the porosity, and that turns out to be 0.571 meter per day. So if you know the actual velocity, then what we can do is we can use the distance, that's 500 meters, and then divide that by the actual velocity. So that turns out to be 876 days, which is around 2.5 years. Okay, so if you look at this problem here, even for a distance, a short distance of 500 meters, it's going to take 2.5 years for the pollutant to travel for this distance, right? And then I think this is very reassuring, right? For example, if there's a pollution spill in Colombia, right? We know that in Rolla we use groundwater, right? So now we know that Colombia is pretty far away from here, right? From Rolla. So let's assume that it's 100 kilometers away, right? And then we know that for 200 meters is taking 2.5 years. Then 1 kilometer is taking 5 years, right? And then 100 kilometers, that's going to take 500 years for the pollutant to reach to Rolla. So basically, this is negligible, right? So while it's being transported, it's also getting diluted. So then people will be less concerned about the water quality, right? At a pretty far away distance. So there are also other approaches to deal with these pollutants. For example, if it's just the spill of some acid or base, you can just add in some other chemicals to neutralize them, right? Or another easier way to, let's say, to mitigate or not to solve this problem, but to guarantee that the water quality is still good, is that we can just build another well upstream of this well, right? Because we know that the groundwater is flowing from higher location to a lower location. So if you build another well upstream, then the pollutant is not going to go this way, right? So in this situation, we can still take the groundwater and not getting affected by these pollutants. Okay, so this is the end of the hydrology. So in terms of the hydrology section, we learned some concepts, right? And we also did some calculations, especially on the hydraulic conductivity, how fast the water is going to flow in the groundwater. And as you can see, the hydrology is mainly dealing with the groundwater, right? Well, for the water treatment or the wastewater treatment, most of the time, people are actually using the surface water, that is the river water or the lake water, okay? So because of that, we need to know what are the major pollutant sources, right, into the surface water. So this is about the water quality management. This is a new chapter. And first about the sources of these pollutants, we can categorize them into 2 types. So they can be the point sources and non-point sources. So the point sources, I think both of them are pretty easy to understand, right? The point sources are mainly just sewage water. So the wastewater coming out of the residential area or coming out of the industry, they can contain a pretty high concentration of the pollutants, right? And after we basically emit them or discharge them into the natural water system, there's going to be a physical mixing. Right, so I think we did some calculation earlier in the mass balance, right? So we have to find out what is the final concentration of these pollutants. So these are the point sources, and there are also non-point sources. And I think agricultural emission is a typical example of non-point sources. For example, if we have we know that near the Mississippi River, there are a lot of farmlands, right? So there are very, let's say, they have a lot of resources on groundwater, right? So let's say we have farmlands nearby, right? And we can introduce, typically people will introduce, let's say, pesticides or fertilizers to the farmlands, right? And we know that these chemicals can just flow with water, and then they can get into the groundwater. So if you just look at the surface, right, of let's say we grow some crops in here, right? And these chemicals, these contaminants can get further down into the groundwater. And then if you have the river nearby, right, if the river is located at the lower position, and we know that the water is going to get flowing into the river. And under this situation, it's not point sources anymore, right? It's basically the pollutants are coming from everywhere. And now it's more difficult to deal with the pollutants here, right? The only way is, let's say we use less of the fertilizer or less of the pesticides. But for the point sources, it's relatively easy to deal with, right? So we can use the wastewater treatment process to lower down, let's say, the concentration of heavy metals or the concentration of the organics, so that we can better protect the ecosystem. So this is about the sources of these pollutants. And there are a few types of typical pollutants that are existing in the natural water system. So for example, there can be metals, there can be, let's say, the salts or some pathogens and so on, right? But the most important one is actually the oxygen demanding materials, okay? So this might sound a little bit new to most of you guys, right? So the oxygen demanding materials, or the related definition of the dissolved oxygen or oxygen demand is let's say, a fundamental definition in environmental engineering. Okay, so here I'm showing you a picture. So probably this is a nearby like a seaside, right? But there are a lot of trash in here. So if I ask you, so how likely it is that the water can contain some fish in here? So the answer is quite obvious, right? It's very unlikely that there will be fish in there. But why is it? What is the reason for that? So you may say, well, it's probably because of the smell or the odor, or maybe the trash is too dense in there, so the fish cannot easily flow in there. But actually, the true answer is because of oxygen, okay? So basically in this water here, the dissolved oxygen is too low. So people also call the dissolved oxygen as DO for short, okay? So it turns out that actually most of the living species in water, they have to rely on oxygen. It's just like human beings, right? We can breathe in the oxygen just from the air, but for the living species like the fish or frogs in the water, they have to rely on the dissolved oxygen in the water. But as a matter of fact, the oxygen has a very low solubility in water. So if you can imagine, let's say we have a 1 liter container, right? For example, a kettle at your home, right? If you have 1 liter of fresh water, and if we put it under 25 Celsius and 1 atmosphere, the maximum oxygen that can get dissolved in this 1 liter of water is just 8 milligram. So basically the maximum dissolved oxygen is 8 milligram per liter, okay? So we know that for 1 liter of water, right, that's 1 kilogram of water. Okay, so for oxygen mass, that's just 8 milligrams. So basically that's 8 ppm of oxygen. So we know that 1 milligram is 10 to the minus 3 gram, and further 10 to the minus 6 kilogram, right? So that's why you have 8 ppm of oxygen in the water. So this is a very low concentration, right? And actually it's quite surprising that the fish can rely on this very low concentration of oxygen to sustain themselves. So because of this low oxygen or low concentration of the oxygen in the water, so the water system is becoming very fragile, because as we know, there are a lot of organic pollutants that we put into the water, right? So there can be a lot of organics, just like the trash in here, right? So there can be a lot of organics, and we know that organics are mainly composed of carbon, hydrogen, and oxygen. So once the organics gets into the water, they're not going to stay there forever. And as a matter of fact, there are a lot of microorganisms that can consume these organics, okay? So they can just go through respiration, right? So to decompose these organics and then convert them into carbon dioxide and water. But this reaction here, this respiration comes with a price. That is, you have to put in oxygen to this process. So basically, these microorganisms also populate themselves based on these organics, right? But they have to consume the oxygen in there. So now it comes into the problem, comes with a problem that if we put in too much of the organics into the water, then these microorganisms are going to consume them. And it's also going to reduce the dissolved oxygen concentration in there. If we put too much of the organics in there, then it's going to consume all of the oxygen. So basically DO will get to zero. So once it gets to zero, it's going to wipe up all the living organisms in the water, right? Not even like shrimps or lower level of aquatic life, right? Not to mention these fish or other higher forms of aquatic life. So basically, it's the oxygen that's wiping out it's a lack of oxygen that's wiping out all the different lives, right? So that's why these organics or these dissolved oxygen has to be closely monitored for the natural water, let's say the river water or the lake water. So related to the dissolved oxygen, there's also a definition called the oxygen demand. Okay, so people also call them as OD. So the oxygen demand is just how much oxygen the organics are going to require, okay, in order to decompose them. Let's say if we put in some sugar or some proteins, right, into the water, right? So those organics are going to demand oxygen, right? So in order to oxidize them, they're going to reduce the dissolved oxygen concentration. So if the oxygen demand is too high, let's say if the OD is above 8 milligram per liter, then we may have a problem because if the OD is higher than 8, we know that the maximum concentration of the dissolved oxygen is 8. So what it means is that no matter what happens, right? So the oxygen or the DO, dissolved oxygen, is going to drop down to 0. So it's going to wipe out all the living species in the water, right? So it turns out that for the industrial wastewater or the residential wastewater, there can be a very high concentration of the organics. The oxygen demand is typically, let's say, in the hundreds. So some of them, let's say, so the meat plant, right? So when people produce meat, so we know that there can be a lot of waste getting generated and wastewater. So the oxygen demand can even be higher than thousands of milligram per liter. Okay, so we know that under this situation, we can't directly dump the wastewater into our natural system because it's going to reduce the dissolved oxygen to 0, right? So that's why there is strong regulation on how much of this wastewater can be dumped into the river or streams, or regarding the flow rate of the wastewater. So we know that in terms of the physical mixing, right? So the wastewater can mix with the mainstream there, right? So if the flow rate here is too high, then it's going to basically make the oxygen demand to be very high, right? If it's larger than 8 milligram per liter, right, then we have a problem. But if you carefully control this flow rate so that it's a very small fraction of the flow, then maybe we can still maintain the oxygen demand to be below 8 milligram per liter, right? So the at least lower level of living species can be there. And then that will also support the reintroduce of the other living species into the river, right? So now we know that for these polluted water, there's no fish in it, not because of the smell or color or odor. It's actually mainly because of the lack of oxygen. Okay, so that's why the oxygen demand is a very important concept. I think in the lab for this afternoon, you're going to do some measurement on the oxygen demand. So specifically, that's called the biochemical oxygen demand. Okay, so we can cover some of these concepts in this class at the end of this class as well. All right, so this is the oxygen demanding material. As we said, they're basically just organics, right? So these organics, when we decompose them, we're going to consume oxygen, right? And then it's going to lead to a reduction of the dissolved oxygen, right? And then harm the ecosystem. So there are other types of pollutants too. For example, the nutrients. We know that the nutrients are essential for all the living species, but for our ecosystem, if you put in too much of the nutrients into water, you also have problems. For example, you probably have heard of the term called the algae bloom or the algal bloom. So the algae are just living species that can use photosynthesis to sustain themselves, right? But it turns out that the algae, well, you may say the algae produce oxygen. Why do we still have the problem? But it turns out that whenever the algae bloom happens, there's going to be a very large biomass, and they can't stay there forever, right? After they consume all of these nutrients, right, they're just going to die off. If they die, then basically they're organics, right? And then the microorganisms are going to consume these organics, right? And then we know that it's similar to the organic waste, right? So the dissolved oxygen is going to reduce, and also these algal bloom, right? They're dead species are just going to contain a high oxygen demand, right? Let's say the OD is high, and then the DO is going to get reduced. And because of that, right, so we have a lower oxygen concentration, then these higher level of living species are going to die off, right? And typically what happens is that for fresh water, let's say the river water or lake water, the phosphorus is limiting nutrient. But by using more of the fertilizers, right, from the farmlands, then you may lead to these algae bloom scenarios, and then it's going to cause these problems. And then for salt water, let's say the seawater, the nitrogen is the limiting species, okay? So that's why the fertilizer also contain the nitrogen, and you probably have heard that the Gulf of Mexico, right, there are dead zones in there. So they're called dead zones, not because nothing lives there. Actually, the algae can live there, but the algae is consuming a lot of the dissolved oxygen. So no other living species can live there, right? Basically, the oxygen concentration is too low in there, right? This is the nutrients. So the pathogens are another type of the pollutants in water. So in the summer, when you go to the seaside, or let's say to some beach areas, right, or nearby the river, you can normally you can see these signs here. So there's no swimming. I mean, the swimming is not allowed in there, not because there are some weird animals or showing around, right? It's actually because of the pathogens. So for these areas, they can be the outlets for the sewage water, okay? So in the sewage water, there can be a high concentration of the pathogens, right? So once you get in there, they probably can get penetrated through your skin, or you can also ingest them through your digestion systems, right? And even if you walk by, right? So there can be some sprayed aerosols. If it's nearby the sea, that's called the sea spray aerosols. So basically, you can form, I mean, over the water, there can be a lot of bubbles in there. And once the bubble bursts, it's going to generate airborne particles that might contain these pathogens inside. So you can even inhale them. So if it's nearby the sea, that's called the sea spray. If it's nearby a lake, that's called the lake spray, right? So for these pathogens, they can even get aerosolized and leads to some toxic effects. But for the groundwater, let's say if you take it from the wells, then it's less likely to be affected by pathogens, right? Because it's so deep in underground, right? And it doesn't have any sunlight. So the bacteria is not going to live there very well. Okay, this is pathogens. Suspended solids. is another type of pollutants that people have to deal with them in the water treatment. Okay, in a water treatment plant. So in the water treatment plant, basically it's the suspended solids has to get removed through some required processes. For example, we can let the water go through filtration, right? So you know that these suspended solids, they're typically pretty small. So they have a diameter, let's say the particle diameter is below 1 micrometer. So if you just calculate how fast these particles can settle down, because you know the gravity, right? So it turns out that they're just going to take years or hundreds of years to settle down to the bottom. So just by placing them there, the solids will not be able to settle down. So that's why you can remove these particles by filtration. You know, their size is 1 micrometer, then we can find some media, let's say the sand, very fine sand media, right? If they have the pore size of, let's say 0.5 micron, then we can remove these suspended solids, right? But nowadays, in terms of the water treatment for drinking water, right? So people also use the method, or a common method that people use is coagulation. Okay, so what people do is that they will throw in some chemicals called the coagulants. Okay, so these are just some chemicals that contain or just some salts, right? That contain some the cations that has a high charge number. For example, aluminum ion or ferric ion. So basically, you can put in aluminum sulfate or ferric sulfate. So the main reason is that for the suspended solids, once they get dissolved into the water or once they get suspended in the water, these solids tend to carry a negative charge. So for these ones, right, suspended solids, they will carry a negative charge. So if you have a cation that has a very high positive charge, then they can attract each other. So basically, you're going to go through the coagulation process where the particles can just collide with each other to form a larger particle. And then after that, people will use the flocculation. Okay, so this is flocculation, right? To grow these particles so that they're grown into flakes or let's say branches, right? So to further make these particles larger. So now they're large enough and then you can settle them down. Okay, so the coagulation and flocculation are a connected process. Okay, so flocculation happens downstream of coagulation in the water treatment. So we can either use filtration or this coagulation flocculation method to remove the suspended solids. Salts are a typical pollutants too, right? You may say that, well, this ocean water is salty, right? Contains a lot of salt. But for the fresh water, let's say the river water, the salt is not so good, right? Especially with some mines, right? For example, this is a metal mine, and this is especially for iron, right? And if you have the ferric ion in the water, then you're going to have these orange color or red color, right? So these ferric ions are going to lead to the hardness of the water, right? So basically, once you boil the water, you can see some sediments in there, right? That's the ferric ion is a typical hardness ion that we have to remove in the water treatment process. Pesticides, right? This is quite important to the water quality too, right? People use pesticides in agricultural activities to kill the basically the pests and also the weeds, right? But by introducing them into the groundwater, they're also harmful to other living species, including human. right? So we have to limit the usage of these pesticides and also try to remove these chemicals in the water treatment. And less likely, that's the pharmaceutical and personal care products, right? So these are the species coming out of the human activity, let's say the chemical engineering, right? So especially for the sunscreen, I'm not sure if you read the instructions in detail. So normally if you flip it to the back, you can see that most of the sunscreen nowadays contains zinc oxide nanoparticle in there. So basically it's because these nanoparticles has very good light scattering properties, optical properties, so that they can scatter light, basically to reflect the radiation back. Okay, so in this way, you can protect your skin. So these nanoparticles, they're not going to penetrate your skin, but once you ingest them, let's say you accidentally put it in your mouth, right, or you inhale them, they can be toxic, right? So that's why if these personal care products gets into the water, let's say the river water, it can get picked up by the fish, right, or other living animals, and there can be a bioconcentration process. Remember that chemical species, right? So in the eggs, right, or in the higher, basically for animals higher up in the food pyramid, these chemicals can get concentrated in the body. So I remember that a few years ago, before the pandemic, I went to Cancun for a break, right? So the place was very nice, but we couldn't bring any of our sunscreens to those forests or reserve areas. That's mainly because the living species or the ecosystem is very fragile in there, and by introducing these chemical species into those ecosystems, that the animals might get affected, right? The living species or the ecosystem can get damaged. So I think this is quite similar in the United States too. So for some national parks, these sunscreens or other types of like personal care products, they are just limited or banned in those areas, right? Metals are a typical let's say water pollutant too. So especially in Missouri, we know that we have quite many metal mines, and we know that we are here, right? So Phelps County, and then just so basically nearby us, there are a few metal mines, and what we want to prevent is that we don't want these metals to get leached into the groundwater or river water, because it's quite difficult to remove them, especially the heavy metals. Right? If it's ferric ions or those hardness ions, we can remove them through the softening process, right? But if it's heavy metals, then it's going to get pretty difficult to remove them. So for all of these chemicals or these pollutants that I introduced earlier, they are chemicals, right? So heat is another type of pollutant, but it's not a chemical. Right? So here I'm showing you some water towers that's being used in the power plants, right? So we use water towers mainly because we have to use steam to generate power, right? So you boil the water, and then the steam has a very high pressure, right? You can push the turbine to move. But even after you use that power there, the steam is still very hot, right? So you have to find a way to cool it down. So the method we use is to use the water tower, right? So the cooling tower to do the heat exchange between the steam and the natural water, right? So that's why for a lot of these power plants, they're built nearby the river or nearby the sea, right? So you can directly take the fresh water, right? The cool water, and then do the heat exchange here. That's also why from the cooling water here, right? You can see these smokes coming out. So actually, these are just water vapors. All right. So these are not the flue gas coming out of coal combustion. This is just water vapor that doesn't have pollutants inside. So to prove these power plants are always built nearby water, right? So I'm showing you two major coal-fired power plants in Missouri. So I think maybe some of you are familiar with these power plants too. So for example, we have the Lavalier power plant. This is just west of St. Louis, right? So you can see that it actually takes the water from the Missouri River, and you have a, let's say, the sewage or dump, right, of these water that's after the heat exchange in the tower here. Okay, so another major power plant in Missouri is the Iatan power plant. So this is built between Missouri and Kansas, and this is also taking the Missouri water. Okay, the Missouri River water here. So basically, it's built nearby, and it can directly take the cool water from the river, go through the heat exchange, and introduce the warm water into the river. So then we need to be careful. We don't want to raise the river water temperature significantly, because all of the living animals in water, they have their temperature zone there, right? You don't want to harm the ecosystem in there. So basically, because of that, there's also regulations on how much or what is the flow rate of the wastewater you can dump back into the river, right? So these are all the common types of pollutants that we're going to, that people have to deal with in terms of the water quality. So as we said, the oxygen demanding material is a pretty important type of the pollutants. So in this class, we're just mainly going to deal with the oxygen demanding materials. Okay, so basically we know that for the polluted water, there's no fish in it, not because of other chemicals, just because of these oxygen demanding materials that's reducing the dissolved oxygen down to zero, right? So that's going to wipe out all the living species in the water. So that's why for the water quality management, let's say the EPA, when they monitor the water quality, what they will do is to measure what is the oxygen demand. Okay, so remember, this is oxygen demand. So they will measure what is the oxygen demand for all the chemicals in the water. Okay, so let's come back to this comparison here. So if we know that the oxygen demand is very high, right? If it's higher than 8 milligram per liter, right? So basically it's higher than the maximum dissolved oxygen, then there's no fish, right? So if the oxygen demand is lower than the maximum dissolved oxygen, then there may be fish, right? So this is not a certain thing, but we want to make sure that the oxygen demand is low for the wastewater, right? So in terms of the oxygen demand or the OD, there are different ways to characterize it, right? So there's a term called the theoretical oxygen demand. There's a term called the chemical oxygen demand, and then the biochemical oxygen demand. Okay, so different oxygen demands are going to have different ways to characterize it. So due to the time limit, I'll just briefly introduce the biochemical oxygen demand, because this is related to the lab session this afternoon and tomorrow. Okay, so the biochemical oxygen demand, the way people measure it is, let's say we can take a sample of the river water or the wastewater, right? And then put it into a bottle. So typically these bottles are going to have a controlled volume, let's say 1 liter in there, right? So what people can do is we can just introduce some bacteria inside. So these bacteria or these microorganisms are just what's being present in the natural system, in the soil. Okay, so what we can do is we can measure the dissolved oxygen before we introduce these bacteria inside, and measure the dissolved oxygen after, let's say, 5 days. So as we said, the maximum dissolved oxygen is 8, right? For example, at the beginning, the dissolved oxygen, let's say if it's 7, and then after 5 days, if it turned out to be 2 milligram per liter, then we know that the biochemical oxygen demand in the water, people typically use BOD 5 because we use 5 days, is 5 milligram per liter. Okay, so basically the organics that's in the water here is going to consume 5 milligram of the oxygen, right? This is the biochemical oxygen demand, how we define it. But as we said, in wastewater, the biochemical oxygen demand can be very high, right? Like the butcher house, and it can be thousands of them. So what people do is we can dilute this wastewater first, You can dilute it by several times, right? 100 times even, right? And then measure that. So if you turn out to be that the BOD 5 is 5, and then you multiply it back the dilution factor, for example, 500, and then you can get the biochemical oxygen demand in the, like the, let's say the sampled water, right? You can get 500 milligram per liter. So this is the idea of how to measure the BOD. I think you will get more practice from the lab sessions this afternoon, okay? So that's all for this class, and let me know if you have any questions, all right?